Hey everyone, welcome back to my question show. Once again, you write down questions anywhere across any of my videos. I see everything. I gather a bunch of them up and I'll answer them here. People asked if I could see questions that you crumple up and throw in your garden. I cannot, but I can see the ones in your dreams. So, now last week we talked about this idea of the supermassive black hole at the heart of the Milky Way and to figure out which way it's spinning, what's its alignment. And I mentioned that there were some papers that showed that it actually has the same spin alignment as the rest of the galaxy, but I couldn't figure out which direction it's going. So I reached out to an expert. I reached out to Dr. Avi Loeb, who is with the Harvard Smithsonian Center for Astrophysics, one of the people who's working on the Event Horizon Telescope and Breakthrough Starshot and other things. We've interviewed him here, and I asked him the question, and here's what he had to say. We don't know confidently how much spin Sagittarius A star has and at which direction it points. Usually, the rotation axis of supermassive black holes have nothing to do with the host galaxy because the black hole is fed by gas swirling closer in at some completely different orientation. So one of the premier experts in this exact subject isn't sure which direction the black hole is spinning. So I think it's safe now for me to say we don't know. All right, let's get into the questions. C4. Hey Fraser, great video as always. I read an article a few months back about the long-term, tens of millions of years evidence of human existence if we were to ever go extinct, and it got me thinking. Geostationary satellites seem like an obvious way to leave evidence for our existence since they have little to no drag effects. But I have no idea what their long-term altitude stability is like. Over many thousands or millions of years, would every satellite eventually crash back into Earth or be sent into deep space? Or could any orbit around Earth maintaining over a very, very long time? Yeah, great question. The geostationary satellites, these are the ones that orbit at a distance from the Earth where their orbital period around the Earth is 24 hours. And so from our perspective here on Earth, they maintain a perfect spot in the sky and they remain there all the time. Now, these satellites actually do have fuel. They have a specific amount of fuel that they have to maintain, really just to maintain their position in this one spot. So they're being influenced by the sun and being influenced by the moon. They're being influenced by the shape of Earth's gravity well. They're being influenced by other planets. And so they are constantly shifting around in their orbits a little bit. And so they have to use this fuel to bring themselves back to this exact perfect spot. So when they run out of fuel, they're going to start to drift. And they're going to not be directly over one spot in the sky. Their orbits will get a little bit more elliptical and they will change over time. But you're exactly right. There's no drag that's pulling it down. They're not passing through the atmosphere of the Earth. So they're not going to be pulled back down into the Earth. They're going to go for however long they can just hang out there until there's some amount of sort of enough perturbations from their orbits that they do get kicked out. Maybe some three-body interaction with the moon, and their orbit over tens of thousands or millions of years changes to the point that they get caught in the moon's gravity and then kicked out of the Earth-Moon system entirely. So really, they are one of the best places to look, one of the best ways to say that, yes, indeed, that human beings, there was an advanced civilization here on Earth. And yeah, if we went out into space and we detected satellites orbiting the Earth, that could have been from a civilization that was before us tens of millions of years ago. It's a crazy idea, and it should be one of the first things that we look for when we search other planetary systems. If we can ever get to that point, look for the satellites. That'll tell you if anyone was ever there. People noted the birds last week, so that's a Stellar's jay that's yelling at me up above, because I am actually standing in the bird feeder, which is also our deck. Arcus. Wouldn't it be possible to use the heat of Venus to one advantage and convert it to electricity, then to cool your rover? So this was a question on the episode that we did about the kinds of rover concepts to explore Venus. And I got a bunch of people saying, what about the air? So yeah, we're going to do an episode about balloons and gliders and airplanes and ideas for exploring Venus's upper atmosphere. But we just wanted to focus on rovers. So this question, which is that why can't you use the heat, right? If it's so hot on Venus, why couldn't you use that heat to power your rover? And the problem is that you can only use heat power when there's a difference in temperature. And unfortunately on Venus, the temperature is exactly the same no matter where you go across the whole planet. Whether it's day, whether it's night, whether you're close to the equator, whether you're close to the poles, it's the exact same temperature. So you don't have this temperature difference that you can exploit. If you did have a big temperature difference, say, that's how a heat pump works, is that you can exploit temperature differences between the surface and deep underground to be able to extract heat or cool your house. So that's why you can't use the heat from Venus. Carlos Saiva. I find the idea of only Earth having evolved multicellular organisms to be practically unacceptable as a rational concept, even on a pessimistic statistical scenario, considering there's billions of stars with possibly many more planets, and there's always the good possibility that most stars have planets in the habitable zones. I think it reeks of local provincialism to think that only Earth alone holds the distinction of having multicellular organisms. It's pretty snobbish to think that we're so unique, if you ask me. You are describing the Fermi paradox, right? Like, this is the point, that when we look out into the universe, we see 100 to 400 billion stars in the Milky Way. We see 2 trillion galaxies across the entire universe. Each one of those stars, we are pretty certain, has multiple planets, and many of those planets are going to be in the habitable zone of their parent star. The moment that life could form on Earth, it did. So life should be everywhere. Everywhere. And yet, when we look for it, we don't see it. And that is the crux of the Fermi paradox, is that it is insane to think that we are the only life forms in the universe. It's crazy. And yet, we don't see them. That's why it's a paradox. That's why it's so maddening. And that's why we get so, just your mind blows and you sort of get yourself into these contortions every time you try to think about it. They should be everywhere, yet we don't see them. Where are they? So, I don't blame you that it seems insane. And yet here we are and we don't see them. Dave Dangerous, 74. I have a question. What type of rocks are there on Mars? For example, would I be able to have granite worktops on my kitchen on Mars? Buy a quartz watch made on Mars? So, I'm not a geologist, so please bear with me. Geologists describe sort of 3 kinds of rocks, right? There's igneous rocks, the ones that are produced by volcanoes. There are sedimentary rocks, the ones that form in layers in water or bacterial, like life forms can produce this. And then there's metamorphic rock, which is rocks that have spent started out as igneous and then went through the earth and went through another cycle and then came back out and they're changed. Granite, quartz, things like that. And on Mars, it's thought that, the entire landscape is igneous. You have no problem finding volcanic rock. And now with the discoveries made by Curiosity, where liquid water was acting on the surface of Mars for long periods of time, they're finding the kinds of rocks that are going to be sedimentary. But it's expected that there will be very little metamorphic rock because you just don't have that kind of active volcanism that we have here on Earth. Now, it might have happened a long time ago, and it's thought that maybe there's going to be metamorphic rocks deeper inside the core of Mars, but for the surface, you're not going to find a lot of metamorphic rock. One idea that was proposed that I saw was that you could have impact craters from asteroids, and that would generate potentially various kinds of metamorphic rock where the impact happens. So that could be a way, but they're going to be very rare. Your granite countertop on Mars is going to be very rare and very valuable. So, so maybe explore other options. Lava rock makes a really nice countertop. Nolan. I'm still surprised that I have not heard of any companies applying the printed solar technology directly onto roofing materials, rolled roofing, metal roofing, vinyl, plastic roofing. Just print the solar right onto these materials and you become good to go for roofing installation. A simplistic approach like this is very likely what would be needed to get a large-scale adoption and cheaply made solar. The real trick with this, however, would be figuring out how to give a fresh solar coat when the cells degrade. Yeah, in the last episode of The Guide to Space, I mentioned these Perovskite crystals. And in that I actually mentioned one very recent, like that day, some researchers from Rice University had developed a methodology to remove some of the impurities from the Perovskite crystals. And the challenge with these crystals is that they degrade very quickly under moisture and oxygen, under Earth conditions. But they're coming up with ways. And so they had developed a method where they had some samples that were sitting outside in Houston for a couple of months and they were still working. So I think that this is a practical materials challenge. It might just be that you create the material and then you overlay it with some kind of plastic or something like that that seals it in, and then maybe you're exactly right. Over some period of time they degrade and then you tear them up and you put new ones on. And that is the dream. And that's why everyone is so excited about this technology of solar cells. They're less power than the photovoltaics, but you can just spray on this material onto the side of a building or on the top of a house, and suddenly the whole thing is one big solar panel. And then you hook up your electrodes and you start to generate power. You could spray a car with it, and the whole thing is a solar panel. So obviously the uses of this technology are tremendous, and we are just right at the cusp of people figuring out how to use it. And hopefully, maybe the developments to make it work in space will have their applications back on Earth, like so many other technologies. Christian J99. Are planets with polar orbits possible? Are there any known planets with interesting or unique inclinations? Yeah, so here in the solar system, all of the planets and Kuiper Belt objects are orbiting in what is called the plane of the ecliptic, and that is the plane that matches the rotation of the sun. And that's because they all formed from one big solar nebula, and it turned into this flattened disk as it formed and flattened out, and then all the planets formed in that disk. And so it would be really weird to see a planet that was on a polar orbit, something that was going completely above the sun. Now, it's not impossible, but you would need some kind of mechanism to find it. You would need to be able to see, maybe there's some kind of three-body interaction where a planet did a bank shot around Jupiter and then somehow got swung up into some kind of polar orbit. It would probably be highly elliptical. So we don't know of any here in the solar system, but in fact, the searches for some of the most distant objects in the solar system, the Planet Nines and other Kuiper Belt objects, really, astronomers have searched the plane of the ecliptic quite well. And so if there are any other objects out there, they're probably going to be above or below the plane of the ecliptic, and they're not going to be perfectly in the rest of the plane. So there was a press release earlier this year where astronomers had found an exoplanet which actually did contain planets that were orbiting in a super weird polar orbit. So they've actually found examples of this in other solar systems, just not here in ours. Rocco V. 1% the mass of the galaxy? That's huge. No way that's right. Yeah, last week I said that the mass of the supermassive black hole at the heart of the Milky Way is just 1% of the mass of the galaxy. The bulk is actually the dark matter halo that surrounds the entire galaxy. And a bunch of people pointed out that, in fact, the mass comparison of the supermassive black hole to the rest of the galaxy is way less than that. So the exact number, I ran the math, I took the mass of Sagittarius A star, divided it by the mass of the Milky Way, and multiplied it by 100 to get the percentage. And the number is 0.00084%. So it's a fraction of a fraction of a fraction of 1% of the mass of the Milky Way. So I won't make that mistake again. And it's amazing how little. So the supermassive black hole is not the anchor of the Milky Way. It is not what everything orbits around it. It is just one, very important, very massive chunk of the galaxy, but it is not what everything is orbiting around. Vignesh Gopinath. You would explain how ISS have to keep track of space debris, but what and how spacecraft like Voyager or any mission tackle micrometeorites? What would happen if SpaceX Starship hit by micrometeorites on the way to Mars? Now, it depends on the size and mass of the micrometeorite. But when we're thinking about micrometeorites, we're thinking of things that are really grains of sand. And they are slamming into all spacecraft all the time. You can see pictures of the main screen from the space shuttle that shows all of the debris impacts that happened after a single mission. Some of them a little unnerving. You can see chips taken out of the solar panels on the International Space Station. These things happen all the time. Now, if a micrometeorite actually punctures, say, the International Space Station or a spacecraft, in many cases, it's not that big of a deal. You're going to get a tiny little hole on the side of your spaceship. Hopefully it didn't hit anybody, right? That would be a problem, but still, it's going to puncture right through the ship and out the other side, and you're going to have two tiny holes in your spaceship. Now, people sort of imagine this explosive decompression. The moment you get this tiny little hole, then the whole thing explodes and it's gone. But no, a tiny little hole, you could stick your finger over the hole while the air is escaping out of your spaceship. Give it a couple of days or maybe weeks and your air is going to go out into space, but it is not really that dangerous. So they're going to assume this is going to happen. They're going to be ready for it. Hopefully the outer shields of the spacecraft are there to be able to prevent any kind of micrometeorite impact that, they use like either a rigid structure or they have various kinds of Kevlar blankets that will absorb the impact of these things and stop them from even making it into the spaceship. And if they do, then they'll have ways to repair the patches. And someone had mentioned this great idea that you can have like a balloon that floats. Oh, this was science fiction? Anyway, that you have a balloon that floats around inside your spacecraft. And then if you get an impact, then the air starts to move toward that. Then it just sort of floats over and blobs up against the hole and maybe even breaks and is filled with glue and automatically repairs it. So I wouldn't worry that much about those micrometeorite impacts. Now, a serious chunk of debris, something, I don't know, fist-sized, suitcase-sized, car-sized, then you've got a bigger problem. But for the kinds of material that they're most likely to hit, you don't have to be worried about it. Sicknicks. Why is a black hole still a black hole if it loses enough mass to go below what a black hole could form in the first place? Like, why do stellar black holes not evaporate and turn into an object without an event horizon when they get below the mass of an object that a black hole will be formed? Black holes are defined by their density. So as long as you've got a bunch of material compressed into a size where the escape velocity from this object exceeds the speed of light, you've got a black hole. And once it becomes a black hole, it will never not be a black hole. Now, this idea of Hawking radiation, that black holes can evaporate over vast periods of time, just means that the black hole is going to have less and less mass over time. But it will still remain a black hole until the last moment. Until it's just a small collection of particles, it's incredibly hot, it gives off a blast of gamma radiation, and then it's gone. So there's no point where it's like it's holding itself in and then it reaches some minimum mass and then it pops up into like a neutron star or something like that. Once it goes black, once it turns into a black hole, it is never going to return to the laws of physics as we understand them. Tim Robinson. Hey Fraser, great show as always. I was wondering, are all sci-fi universes static? I've noticed that every time a ship drops out of warp, FTL, etc., they're always traveling at the same velocity as nearby objects, like planets and ships. Even if they meet by accident, they never have to accelerate or decelerate, and doing this automatically would mean infinite acceleration. What? Science fiction does something that's not realistic? I'm shocked. Yeah, when you think about the solar system, you think about the Milky Way, like think about the Earth. Like right now, you're standing on the Earth and the Earth is turning and you are going 1,000 kilometers per hour turning around with the Earth. But the Earth is moving at 30 kilometers per second around the sun, and all the planets are moving, and the sun is moving, and I forget, 230 kilometers a second or something around the Milky Way. And so everything is moving. And so if you're going to go from one star system to another, you actually not only you have to make the jump of however many light years it took to get there, but you then have to match the velocity of the star in whatever frame of reference you're now in. But it's magic. So who cares, right? Like, that's the thing. Yeah, if, to be realistic, after you fire your warp drive, and then you want to be realistic, then when you arrive in the system, you're going to need to have some other method, some impulse drive that will allow you to calculate the orbit and match the orbit of whatever, the velocity of the object that you're trying to go into orbit around. And if you play a game, like say play Kerbal Space Program, everything's orbits. Right? Everything is moving in various kinds of orbits, and you think in orbits. It is not about taking a direct line. That said, if we get to some point where you've got power to spare, then you don't have to worry really about orbits anymore. You just point in the direction of the thing you want to get to, and you fire your super hyper plasma drive, and you just fly there. And then you just fix whatever orbital changes you need to as you need to, and you don't really worry about it. And to sort of think of an example, when you're here on Earth, you're going 1,000 kilometers per hour, following, if you're at the equator, you're following that Earth at that speed. And yet when you get to the North Pole, you're going 0 kilometers, so you're turning once every 24 hours. And so you've gotten rid of 1,000 kilometers per hour of velocity to go from the equator to the pole. Well, how did you do it? You did it bit by bit as you drove directly towards the pole. And you didn't think about or care the fact that you were getting rid of 1,000 kilometers per hour velocity. And that's the way super futuristic science fiction magic spaceships are going to work. Marie Edwards. Hey Fraser, if we do colonize Mars, what type of time system will the Martians use? Will it still be 24-hour clocks based on Earth time, or will they stretch the seconds to be a full 24-hour Martian day? Yeah, in case you didn't know, a day on Mars is like 24 hours and 39 minutes. So it's not the same length as a day on Earth. It's surprisingly close, 39 extra minutes every day, but it's not exactly. And so time on Mars is going to work differently from time on Earth. And it's not just going to be like daylight saving time. Like every day, the clocks are going to differ. And in fact, the people who worked on a lot of the Mars spacecraft, people who worked on Spirit and Opportunity and Curiosity, they live on Mars time. So they set their clocks forward every day and they arrive at work a little bit later so that they can work during the Martian day to be able to see where they're going and analyze the science data. And then over time, as the science builds up, then they can sort of shift back into a regular Earth schedule. So what will the Martians do, right? The one option is they add a tiny little bit of time every hour, so they still only have, so a 24-hour watch will work, or every day is just a little longer. And I don't know what they're going to do. I don't know what the solution. If you want to have a day be 24 hours long, then you'll just change it so the time doesn't work exactly right, but you'll always know what it is time on Earth. Or will they want to specialize in or focus on having time on Mars match time on Earth until you just always live your life based on Earth time. So even though you're living on Mars, you'll be calculating yourself based on, say, Greenwich Mean Time or something like that. I don't know what the solution is. It's just going to be one additional headache to living on the red planet. Einite. Hey Fraser, this is my question. Can you use the light dipping technique but inverse to theoretically find Planet 9? For example, you could observe the sky either 360 degrees or just the orbital plane of our solar system to find dips in light from galaxies that Planet 9 might cross paths with. Would this be possible? And if so, practical technique to look for the planet. So we talked about this idea of the transit method, that you can be outside a star, you can watch as a planet passes in front of the star, and then you can watch how the light from the star dims, and that tells you that there is a planet there. And astronomers use another technique that's kind of similar and sort of what you're talking about. It's called an occultation. And so what astronomers will do is and usually it's predicted, they know this is going to happen. So they know that there's going to be a time when, say, Pluto is going to pass directly in front of some star, usually a fairly faint star. It happens so rarely that it's still a big event when it's going to pass by even a star that you can't even see with your own eyes. And so they watch the star, and then they watch as Pluto passes in front, and they're not seeing really Pluto passing in front, but they're seeing how the light dims as Pluto does. And from that, they can determine, say, what Pluto's atmosphere is like and some other characteristics of it. incredibly useful technique. It's been used to find out a lot of stuff about the solar system. And so I can imagine this technique where you've got some space telescope that's constantly watching the sky, and it is just watching for occultation events all the time. But something like Planet 9, it's going to be moving very slowly, and so the chances that it's going to pass in front of a bright enough star to generate an occultation event is going to be fairly low. One interesting sort of additional piece of research is that the TESS satellite that's finding exoplanets is actually going to be a really good tool for finding Kuiper Belt objects. Astronomers were able to find many of the Kuiper Belt objects that have already been discovered in the TESS data, and they think that in fact TESS could be used to find Planet 9 as well. They sort of have run the calculations, and it should be in there somewhere after TESS has done a lot of observations. So maybe that's another route in a kind of a similar technique, but it's a great idea. Again, those are the questions this week. Thank you everyone who sent them in. I have a great time with this. I hope you do too. If a question pops in your brain while you're watching any one of my videos, write it down. I'll gather them up. I'll answer them here. I'll see you next week.